Okay, welcome to IVPs for ODEs and other cool stuff. All right, so IVP sounds super fancy, but it's honestly just one of these things. Let's do a very simple example. So we have an ODE, which is just y prime equals x. That's the simplest one I can come up with. And you need an initial value problem. So the initial value goes there. Okay, so how would you solve this problem? Well, let's try it. We're going to say, all right, I'm going to rewrite y prime as dy dx, and I'm going to put the dx on the other side, and you may be like, whoa, hold the phone, how did she do that? I'm just showing you. I'm not expecting you to do anything difficult. So any questions that, if you haven't had the prerequisite material to be able to do this on your own, you're just going to solve them on Wolfram Alpha, and I'll show you how to do that. Okay, but if we do this, then we integrate both sides and we get x squared over 2, but then we have plus c, and that's the whole point of having y of 0 equals 3, so that we can go ahead and figure out what c is. In this case, it's 3. Okay? And so when we were at this stage, just a little terminology, this part is called the general solution. That's before you plug in the initial conditions to get the full specific solution. Okay? So this is just the anatomy of one of these specific solution. Okay? So typically what you will be asked to do as a warm-up to an exercise is that you will be asked to show that a particular solution solves a differential equation. You may be asked to start by solving it, but if you can't solve it, you just go to Wolfram Alpha. So for example, let me just pull up Wolfram Alpha for a second. Okay, so what if the problem you want is the derivative of y equals y cubed? And then it should probably try to find a solution, and then it should mess around a little bit and give you a solution, and there you go, differential equation solutions. But you see, it's just a general solution because you have a C1 or a C2 or something in there, which means that's the general solution. Okay? So any problem where you're asked to solve, you just go and ask Wolfram Alpha what the answer is. Okay, so how will it look on paper? Okay, so if the exercise says solve and verify as a first step, before you have to do something numerical to it, you would just plug it in and say, okay, Wolfram Alpha says this. Another way of writing that is c minus 2x to the negative 1/2. I mean, Wolfram Alpha puts a subscript 1. You obviously don't need that if there's just one constant. Okay? And so let's demonstrate. Demonstrate that it's correct. Okay, so then we're going to take the derivative, and it's going to be minus 1/2 to the minus 3/2 times the derivative of what's inside. So lucky for us, this guy wipes out with that guy. We still have a plus and minus sitting out front. To the minus 3/2, and let's just see if that satisfies the differential equation. We also said y cubed. Okay, so what does y cubed equal to? Well, we're just going to cube the, we're just going to change this exponent here to cube that, and we're going to say, oh great, these guys are equal, which is what we were looking for. Yay. Okay, so we've demonstrated that. Warning, sometimes Wolfram Alpha can be a tiny bit wrong. So don't say I didn't warn you. But that's okay, because if the goal is to verify, then it doesn't really matter, because it's kind of like the whole diffie-q ends justifies the means thing. As long as you show that it was right, then you put some of your own effort into it. Okay, so let's go ahead and solve this one and verify Okay, so I'm going to say Wolfram alpha says y equals c plus x squared over 2 plus e to the x. And I say, well, maybe I don't know how they got that, maybe I do, but I'm going to go ahead and take the derivative and see if I agree. It's going to be 2x over 2 plus e to the x, which is x plus e to the x, and I would say that works. Again, you do not have to know how to get these solutions. However, if you recognize these as problems you should know how to do because you've taken the prerequisite material, I do encourage you to use this as an opportunity to review. And if you're in that situation and you're struggling because you just want to remember and you've forgotten, then by all means ask me and we'll go through it together, because I don't want you to miss an opportunity to review your knowledge. Okay? All right, so here's a question. Okay, so beyond asking a computer or another computer for help, how can we tell if an ODE even has a unique solution? So if you have the textbook, I have the purple copy. I think that's version 7, and then in that copy of Burden Fairs, it's theorem 5.4, but it's certainly in any version of Burden Fairs. It is the Lipschitz theorem. So let me write that out for you. Okay, so suppose we have a domain that has, usually I'm going to put like t on the horizontal and y on the vertical. And t is over a fixed closed domain in T, but y is not necessarily on a closed domain. It's probably going to go, it's going to be open or go to infinity or something. But f is continuous on the domain. If f satisfies a Lipschitz condition on D in the variable y, then the initial value problem, blah, 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 has a unique solution in that domain. Okay, so first of all, yeah, just because it has it, it doesn't mean it's going to be easy. So good luck with that. Good luck finding it, and we'll talk about that. But this bit is not talking about whether or not it's easy to find. It's just telling you that you can find it. So I have to tell you what a Lipschitz condition is. Okay, I have a little confession. Every single time I say Lipschitz, this is what I think of. And I walk around the house saying, hey, has anyone seen my Lipschitz conditioner? Just kidding. Well, sometimes I do. But anyway, I can't get that thought out of my head, and I thought I'd share that little joke with you. Okay, so what is the Lipschitz condition really? Well, if your f is defined on our domain, which it is, and our domains are going to be complex, which we need, but I never bothered to check. Okay? And apparently I can't pause this. There we go. I hate typos. Okay, so and a constant L, which is greater than 0, exists for the domain. And what that and the partial of f with respect to y for a fixed t, okay, then it's within, actually for all t's, then f satisfies a Lipschitz condition on the domain with Lipschitz constant L. So I want to think of this t as being frozen a little bit. Imagine t freezes, because that's what it means to take a derivative with respect to y. Imagine t freezes, but then you can move it around to make the derivative as bad as possible, to make fy as bad as you can. And then the thing is, t is bounded, right? So t is on this domain from A to B. So is that going to be enough to make sure that y is bounded? Will y go out of bounds, to say it that way? Okay, I'm gonna draw another picture. I'll sort of draw the picture to go with the next example. How's that? Okay, so here's this example. The derivative of y is 1 plus t times sine of t and y. I meant t times y, sine of t times y. Okay. All right, so what I want you to imagine is first try to imagine where it lives. Okay, so it's going to live, you have t equals 0 over here, and so y of 0 is 0, and this line over here is t equals 2. So the question is it going to go out of bounds? What's it going to do inside this strip? Okay, can he get away? Can he escape? Can y escape? So we've tied it down here. This is where it starts. How bad can it get? Okay, so for example, if I imagine freeze t, and then the question is the derivative that you're going to experience, that f, you know, from this function, is that somehow bounded after you freeze t? And if that's true, if it's bounded for all these t values, you just pick off the worst one and use that as your Lipschitz constant. Okay? So in this case, we have df dy. You can write it this way, or you can write partial of f with respect to y, and this bit here is actually f. Okay, we're going to take the derivative of that with respect to y. So we're freezing y, and so what do we get? We get t squared cosine of ty. How do we get that? Well, t just looks like a frozen constant now. And derivative of sine is cosine times the derivative of what's inside. The derivative of ty, when y is the variable, is just t. So that's why that pops back out again. Okay? So cosine can never go over 1. But this can't go over 1. And so t can't go over 2. So this thing can't go over 4. So this whole thing can't go over 4, and so our Lipschitz constant is 4, because that's the worst that this derivative can get, even though, yes, it's all the way over on this line here, but you have to consider all possible lines of frozen t's all the way through, and then pick off the worst one. So the worst this can possibly be is 4. Okay, so we do have a Lipschitz constant. It is 4, or you could say L equals 4, and all our other conditions are met. So this has a unique solution. So the solution could exist, but does that mean we can find it? No. Just like we had issues with fixed point methods not working unless we had a contraction mapping, we have similar types of issues here. Just because it exists doesn't mean it will be easy to find. But if it is well posed, we have a fighting chance. So in order for it to be well posed, first of all, it has to have a unique solution, which we already showed, but also the system has to be stable to small perturbations. Well, what does that mean? It means if you change the initial conditions a little bit, or if you change the differential equation a little bit, you'll still end up close to the correct answer. It's the opposite of chaos. It means that small changes in the problem cause small changes in the answer. It's easier to give a counterexample. There are some, let's say, polynomials. There's crazy polynomials that wiggle a lot, and that you could essentially use them to create a crypto system. So if I have t going along this way, and every time t changes, my password changes, that's pretty crazy. But I could prove to you I know the password system by pulling a couple points off of here, but somebody who's sniffing couldn't recreate the polynomial from just a couple samples. The weather is a very ill-posed differential equation. This is obvious whenever there's a major hurricane coming over land, because we can watch the maps day in, day out, but they keep changing, right? You'll have the hurricane map, it'll have like this cone, right? It'll have some cone, and we really don't know where it's going to go, but afterwards we could just draw a line and say that's where it went. So that's an example of an ill-posed differential equation. Another thing we can look at is if you look at a direction field where you would put, let's say, y over here and t over here, and we're just going to look at some, maybe one solution goes off like this and the other solution goes off like this, and another solution goes off like this. And so some of the curves that are close to each other to begin with are going to end up being buddies forever, but some of them are just going to go splitting off to infinity, and they'll never see each other again. Okay, so some differential equations are ill-posed and some are well-posed. Okay, so let's say you want to do Euler's method next. That's what we're going to talk about. Okay, we're going to use Euler's method to try to find a solution to your equation. We're going to put our initial condition right here. T naught, Y naught will start right here. And let's say our actual differential equation does something like this. Then the way we label this is the initial condition is actually on the solution. And here's where we'd like to find. We'd like to find y1, y2, y3, and so on and so forth, all the way up to our final endpoint. And if we do a really good job, we'll be very, very close. But we will never actually know the solution, except in a pedagogical situation. We often trace functions we actually know the answer to, and we do that again for pedagogical reasons. If you know the solution, you wouldn't be doing it this way. Okay, so typically you don't know where that solution is, but maybe you use Euler's method to trace out a line. Why am I not able to draw a line with this tool? There we go. And then maybe I draw another line. Okay, fine. It doesn't want me to draw lines. I'm just going to have to draw lines a different way. Okay, so this is this blue line. I'm saying this is my approximation to my solution, and it's not going to be right. I'm going to label these W's, W1, W2, W3, all the way up to Wn. Okay, so the Y's are where the real live answer is, if we could tell. And the W's are where we're hoping the answer is, but it's not quite right. Okay, and then the error is going to be the difference in those 2 points. So my intention is that these guys line up vertically. So let me just line these guys up better so I don't confuse anybody. They should be one directly over top of the other. Okay, so the T's we know. We know T because T is the step we're choosing. We just don't know where the Y goes. Okay, so what we would hope, what we'd really love is if, let's say, this guy is our function, F, or Y, and these guys are our W's, and they kind of balanced out. Maybe we'll end up really close. Like maybe our errors will get bigger and then smaller over time. It probably won't. I mean, we just kind of make the assumption that the error keeps growing and growing, and sometimes we get lucky and it doesn't. Okay, so let's have another example. Okay, so here's an example. Y prime is 2x, and y of 1 is 1. We're going to use a step size of 0.1, and we're going to try to estimate y of 2. All right? And I'm going to show you how to implement Euler's method using this example. Okay? So what we're going to do is we're going to find out what the derivative is at the starting point, and we're going to step out h of 0.1 and see where it takes us. And then we're going to keep doing that. Of course, we pick a question that we already know the answer to, because when we do that, we can do an exact estimate of the error, or calculation of the error, rather. Okay, so you can do this out by hand, and I encourage you to do this whole thing out by hand because it's intended to be done by hand, But I had another thought. I thought maybe you need more practice with Python. So I'm going to show you how to do it on Python. And so I'll leave it to you as an exercise to do it by hand and verify what happened on Python. If you haven't gotten used to using Lambda yet, you should, because we're going to be using it a lot for the rest of the semester. So hopefully you're already comfortable with that. But it just makes your life way easier in these kind of exercises. We've started out with W being 1 and T being 1, and each time we're going to add H to T. And let's estimate what W will be when T increases by 0.1. Okay? So first of all, Y prime at our current W is 2, right? So if we want to multiply by H, it tells you how much additional height we want to get. And so W equals W plus Y prime of W times H. And what's our new W? It becomes 1.2. When I do that, I don't want to forget this, though, that T equals T plus H. So now I have my new T value. Okay? And let's do this again. Let's say for I in range, I don't know, 9. I'm going to say W equals W plus Y prime W times H. T equals T plus H. Print. I want to print which iteration. I may as well print I for my own sake. And I want to print W and T and W. And then actual is what is Y actual at T. Maybe I should say this is the estimate. And maybe I should say this is the T. Hopefully that's enough information. I'm giving I, T, estimate, actual. Let's see what happens. Hopefully this doesn't crash on me. And it seems to do pretty much what I expected, except something went wrong. Now let me pause and figure out what went wrong. I wasn't expecting it to go over like that. Well, like so many bugs, it's easy to find the bug after you know where it is. So if you don't know where the bug is, I want you to pause and see if you can find my bug, because it's a pretty classic stupid thing to do. So see if you can figure out what I did wrong. Okay, now let me reset this. So T is equal to 1, W equals 1. So for I in range, and this time I'm going to have to go to 10, W equals W plus Y prime of what? Not W. That was the crazy part. Okay, and then I'm going to say T equals T plus H. Can I just up arrow to get that print statement back? Apparently I can. Okay, let me see if I agree with that now. Well, I'm not 100% sure, but I think it's right because it doesn't match my notes, but I think the computer's right this time because it looks right now. Okay, so we should be going just under the actual value, and 3.9 is under the actual value, and the first few iterations do match my hand calculations. So this is now in a good state for you to trace through by hand and see if you agree with Python. I'm pretty sure Python isn't the one who messed up. Pretty sure it was me. Okay, so next point. Okay, so we can estimate the magnitude and sometimes the direction of the error. When you start, first of all, you presume there's no error, and then you will make the assumption that with each step, if the previous step were right, you're going to accumulate more error. So here's the official true statement that is somehow meaningless because we don't even know what y is, but that's what our baseline is, right? And this is what we're calculating. Wi plus 1 is what we use to estimate y of t at I plus 1, and that's going to equal to our previous iteration plus h, that's our step size, times f of ti wi, because that's what we have, what we calculate this. Okay, so notice if we say yi, it's another way of writing y at t sub I. Okay, and so we can subtract these guys to find the error, in theory. Okay, so if we call this line A and we call this line B, the next line is A minus B. So I just took whatever's true and I subtracted out our calculation. This quantity here is error. This is our new error. This is our old error. You know that h is our step size. And this quantity here is the difference. It's the difference in the actual slope at t on the actual solution versus what we've been using, okay? And this thing just kind of came along for the ride. This is our error. This is like new-ish error. It's like a new component to our error. Like we already had errors, but now we have more errors adding in, okay? So we're just going to rewrite this a little bit. Okay, so what I'm going to do is I'm going to find some kind of bound on this. I'm going to turn this into a less than equals because it's equals if all these guys are going in the same direction, and it's not necessarily going to go in the same direction, so we're going to just put a less than equals there, and this will make it a little bit easier to calculate, maybe, hopefully. Okay, so they could all go in the same direction. All right, we have this bit here. This is a Lipschitz condition that we talked about a little bit. L. Here's our Lipschitz constant. We know we have a Lipschitz constant or we wouldn't even be here. And this thing is approximately equal to m, which we're going to put in a formula. And so we're going to say F satisfies a Lipschitz condition on a Lipschitz condition L, and we also say, okay, and we're going to bound this guy. Second derivative has to be bounded by something. We're just going to give it the letter m. So the previous thing we just had is going to get rewritten. So our error, this new error, okay, is less than or equal to 1 plus h times L times the old error, and then this new piece, h squared m over 2. Okay, maybe you're asking me where the h squared came from because maybe you noticed that I forgot the h squared in the step above. Let me just go fix those for you. Sorry about that, I forgot the squared. There was a squared. Oh, I did put the squared in there. Okay, good. Yep, all the squared. So there's a squared here, and then a squared here, and then a squared here. Good. I got them that time. Okay, we need one more lemma, which I'm skipping the proof for, and it says that there's some s and t that are positive and real, and we have a sequence A where, yeah, I'll fix the where in a second. 1 plus s, ai plus t, and this is the implicit form of the error. In this case, we're going to use it as an error, but the growth bound. Okay, and is worst growing exponentially at worst, and this is the explicit form of the exact same thing. Whoa, I didn't mean to do that. So, you know, my computer is kind of hard to control some days. E to the I plus 1s times a naught plus t over s minus t over s, and this is the explicit form. That's why we can only use a naught instead of just ai, because we're going back only to a naught. Okay, so we can pop this into our previous expression to get the following. Okay, so when we dump that stuff from the lemma right in, then we get this E stuff right in the middle of our bound, and this mess right here is going to be like Ti minus T naught, something like that, or T naught is equal to A. Okay, so then we're going to get this H canceling out, and we're going to get another H canceling out over here. Do we get any other cancellations? And we do some algebra. And then we get, okay, so after some algebra we get this simplification. And what's annoying? It is annoying that we don't actually know M usually. So, well, sometimes we do. We do in the homework. We do in the homework, and we do in academic exercises, but not in real life. Okay? Okay, so let's do an example. Okay, this is the example we're going to work. We're going to look for a good H to use with Euler's method, and the real answer is you shouldn't be using Euler's method, but that's not the student answer. So what's the student answer? The student answer is, first of all, what is f? So the derivative of f with respect to y, or the partial, is 1. Well, so since we are not really worried about t wasn't really intertwined with y in any way, so this made this easy. So we got out a jail-free card, but now we need M estimate. So you need y double prime bound. So how will we get that? So y double prime is equal to f prime, which is equal to derivative of f with respect to t plus derivative of f with respect to y times y prime, but we're not going to use y prime because what are we using instead? Of course, we're going to use f because that's what f is. So what is this thing? This is just your, your product rule, right? You use this all the time for implicit differentiation and things like that. So we're going to just simplify this. Okay, so we already had f. We had f with respect to t is minus 2t, and we had all these pieces lying around. We can actually solve this, but that's kind of cheating. So let me just guess that that y is less than 100, just for guessing, and then I can adjust it later if I'm wrong. I know that t is between 0 and 2, so I'm just guessing that maybe m is about 100, and so let's see if this makes any sense. Okay, so our total error is going to look like this. It is less than or equal to hm over 2l, e to the L t I minus a. I wrote an alpha, I meant to write an a, minus 1. Okay, let's see if we can, if that m equals 100 makes any sense here. L is 1, h is the thing we want. We want the total error to be, what did we say? 0.01. Okay, and do we have any other information? We had t between 0 and 2. So this can't be bigger than 2. Minus a. A is 0. So this whole thing can't be bigger than 2. Okay, so let's put all these pieces together. 0.01 less than or equal to 100 h over 2. E squared minus 1 is 50 h times 8, which is 400 h. In that case, h is going to be 1 over 40,000, which is yikes. But it doesn't matter. This is the year 2020, so we can try it. Okay, let's just try it. W0, and if we were wrong about y, like this will sort of justify, the ends justify the means, because if y goes bigger than 100, then we'll have an idea of what to try next time. So we're going to try h as 1 over 40,000. It's just a huge number. T equals 0. F is going to equal something like lambda y comma t y minus t squared plus 1. Make sure in Python you never do that. That's not t squared. And then you can do something like this. While t is less than 2, you can do something like w equals w plus h times f, wt, and t equals t plus h. And the answer it gives us, I did this before, but it's something like 5.30546, which is nowhere near 100. So the ends kind of justified the means. We don't have to redo this, and we happen to know the actual result. If we calculate it because we happen to know y is equal to t plus 1 squared minus 1/2 e to the t. So if you figure that out, it's 5.30547. So we're good all the way up to, let's see, 5 digits, like 5.5 digits. So I'm happy with that. Okay, and that is quite enough for one video. Okay, hopefully this will help you get through the homework. And if there's any trouble, as always, just let me know.